A surface integral adds up a quantity over a curved surface rather than over a flat region. Flux measures how much of a vector field passes through a surface, telling us the net amount of flow across that surface. Here is our worked example. We want to find the flux of the vector field, F, which has components 0, 0, and z, through the upper half of a sphere of radius 1, centered at the origin, with the normal vector pointing outward. First, picture this surface. In 2 dimensions, it looks like a circle of radius 1, sitting flat in the xy plane. In 3 dimensions, that same circle becomes the curved dome of the upper hemisphere, rising up to a height of 1 at the very top. To integrate over this curved surface, we first parameterize it using 2 variables, phi and theta, just like spherical coordinates. The x-coordinate is given by x equals sin of phi times cosine of theta. The y-coordinate is given by y equals sine of phi times sine of theta. The z-coordinate is given by z equals cosine of phi. Here phi ranges from 0 to pi divided by 2, since we only want the upper half of the sphere, and theta ranges from 0 to 2 pi going all the way around. Next, we find the normal vector to the surface. In words, this is the cross product of the partial derivative of the position vector with respect to phi and the partial derivative of the position vector with respect to theta. Working through this cross product for a sphere of radius 1 gives a lovely simplification. The normal vector equals sine of phi times the position vector x, y, z. Taking the magnitude of this normal vector, the small surface element, ds equals sine of phi d phi d theta. Now we set up the flux integral. In words, the flux equals the double integral over phi and theta of f dot the normal vector, d phi d theta. Since f has components 0, 0, and z, the dot product f dot the normal vector equals z squared times sine of phi, which is the same as cosine squared of phi times sine of phi. So the flux integral becomes integral from theta equals 0 to 2 pi of integral from phi equals 0 to pi divided by 2 of cosine squared of phi times sine of phi d theta. The integrand does not depend on theta, so integrating over theta from 0 to 2 pi simply multiplies everything by 2 pi. For the phi integral, let u equal cosine of phi, so du equals negative sine of phi d phi. This turns the integral of cosine squared of phi times sine of phi d phi into the integral of u squared du, with the limits swapped because of the negative sign. Evaluating the integral of u squared du from 0 to 1 equals 1/3. Multiplying this by the 2 pi from the theta integral gives a total flux of 2 pi divided by 3. For our check step, notice the flux is positive. This tells us the field F equals zk hat is indeed passing outward through the dome, which matches what we expect since z is positive everywhere on the upper hemisphere.